Hello, students, and welcome. Today we're going to do a quick revision of the chapter on sound. This session will help you cover all the important concepts you need to be really well prepared for your exams. So, let's begin. Let's start with a simple thought. Have you ever wondered, how is the sound of my voice reaching your ears right at this moment? Understanding this journey is, the key to this whole chapter. Okay, so first up, what is sound? We'll be looking at how it is produced and how it travels from one place to another. So, what is sound? Well, very simply, sound is a form of energy. And the most important thing for you to remember is it is always produced by vibrating objects. Anything that moves back and forth very quickly is what creates sound. Now, for this sound energy to get from one place to another, it needs a path to travel on. We call this path a medium. This can be a solid, a liquid, or a gas. That is why we call sound a mechanical wave. It needs a medium. And this is exactly why there is no sound in space, right? Because space is a vacuum. There are no particles for the sound to travel through. So how does this actually happen? Well, imagine a vibrating object. As it moves forward, it pushes the particles of the medium close together. This creates a region of high pressure, which we call a compression. Then, as the object moves backward, it leaves a space, creating a region of low pressure, and we call that a rarefaction. It is this chain of compressions and rarefactions that actually carries the sound forward. Now, an important point here, the particles themselves do not travel all the way to your ear. No, they just vibrate back and forth in their own position, passing the energy to the next particle. And notice, they move parallel to the direction the wave is traveling. This kind of wave is called a longitudinal wave. Please remember this for your exam. Sound is a longitudinal wave. Okay, good. Now let's look at the anatomy of a sound wave, its key characteristics. These are very important. First up is wavelength. The symbol for this is the Greek letter lambda. So what is it? It is just the distance between two consecutive compressions or two consecutive rarefactions. Simple, right? And its SI unit, of course, is the meter. Next, we have frequency. Its symbol is the Greek letter nu. It looks a little bit like the letter V. Frequency is simply the number of complete waves, or oscillations, that pass a certain point in 1 second. We measure it in hertz, or Hz. And then there's amplitude, which we represent with a capital A. Amplitude tells us about the maximum disturbance in the medium from its normal, or rest, position. Think of it this way. A bigger, more powerful vibration will create a wave with a larger amplitude. So amplitude is directly related to the energy of the sound wave. Now, this is a very, very important concept. How do we perceive these characteristics? Well, our brain interprets frequency as pitch. So a high-frequency sound will have a high pitch, and our brain interprets amplitude as loudness. A high-amplitude sound will be a loud sound. Remember this difference. Frequency is pitch, amplitude is loudness. And you can see that perfectly in these diagrams. On the left, look at the high-pitch wave. See how the waves are packed closer together? That's high frequency. Now on the right, for the loud sound, see how the wave is taller? That's a larger amplitude. Notice the frequency hasn't changed, only the height of the wave. Okay, for your numericals, these two formulas are absolutely essential. First, speed of the wave equals wavelength times frequency. That is V equals lambda nu. And second, frequency is 1 divided by the time period, t. Please memorize these formulas. They are very important for solving problems. Moving on, let's talk about how sound behaves, specifically its speed, and what happens when it reflects. Just take a look at these numbers. You can clearly see that the speed of sound is different in different media. It's fastest in solids like steel, a bit slower in liquids like water, and much slower in gases like air. Now, why is that? It's simple, really. In solids, the particles are packed very tightly together, so the vibrations can pass from one particle to the next very, very quickly. You know how light bounces off a mirror, right? Well, sound does something similar. When sound waves bounce off a surface, we call this reflection an echo. Think about shouting in a valley. That sound that comes back to you, that's an echo. But there is a condition to hear a distinct echo. Our brain actually holds onto a sound for a very short time, about 0.1 seconds. So for you to hear your original sound and the echo as two separate things, the reflected sound must come back to your ears after this 0.1 second gap, at least 0.1 seconds later.
So, if we do the calculation, sound has to travel to the wall and back to you. The total distance it travels in zero point 0.1 seconds is about 34.4 meters. This means the distance from you to the wall is half of that, which gives us our magic number, 17.2 meters. The surface must be at least 17.2 meters away for you to hear a clear echo.
So what's different about, say, a big empty hall? In a hall, the sound reflects off many surfaces: the walls, the floor, the ceiling. All these reflections come back to you very quickly, and they all merge together. This mixing and persistence of sound is called reverberation. It's not a clear echo, it's more like a prolongation of the sound.
All right, next up is the spectrum of sound, or the different ranges of hearing that exist.
This table breaks it down nicely. The sounds that we humans can hear are in the audible range, which is from 20 Hz to 20,000 Hz. Anything below 20 Hz is called infrasound. Animals like elephants can hear this. And anything above 20,000 Hz is called ultrasound. Bats and dolphins use this to navigate and hunt.
Okay, so let's look at some practical applications of ultrasound. Why is it so useful? Well, because ultrasound has a very high frequency, it can travel in a very straight line. This makes it super useful. For example, it's used to clean delicate parts or to find tiny cracks in metal. In medicine, it's used for scans to see our internal organs, like when a pregnant mother has an ultrasound. Even hearing aids use advanced technology to process sound and help people hear better. So as you can see, sound is incredibly important. It helps us communicate, explore our world, even look inside our own bodies. Who knows what we'll discover with it next? Okay, that is it for our revision. I really hope this has helped you. Please go over all the definitions and the formulas one more time. All the very best for your exams.